Hello everyone, this is D. Chinna. In this video lecture, I am going to explain about hydrogen emission spectrum. Welcome to our chemistry channel. So it is one of the important topic in atomic structure. So this is from this only, and then after we have Bohr's atomic model and applications of Bohr's atomic model only. Many times they asked questions. So first of all, let us see what is hydrogen spectrum and we continue up to the Bohr's atomic model. So first of all, what is hydrogen spectrum? Here, when you pass the electric discharge through hydrogen gas, so which means here hydrogen gas is filled in this discharge ray tube at a very low temperature and under high voltage conditions, say 10,000 voltage condition and very low pressure conditions. At such conditions, when you do this experiment, when you pass electric discharge through hydrogen gas, it is going to give some light. So that light we are going to send through a prism, and here we are getting a spectrum through a prism, and here we are going to spectrum. This spectrum is called hydrogen spectrum. Actually it is hydrogen emission spectrum. Hydrogen emission spectrum. We already know emission spectrum is nothing but due to de-excitation. Of electrons. Due to de-excitation of electrons, it produces emission spectrum. This is totally hydrogen emission spectrum. In this hydrogen spectrum, there are several lines. So they are Lyman series, Balmer, bracket, Paschen, Fund, and Humphrey series. So here, whenever the electron jumps from any higher energy level to the first energy level, it gives a line in the Lyman series. So from any higher energy level to the ground state or n equal to 1, it gives a spectral line in the Lyman series. So likewise, when electron jumps from any higher energy level to lower or ground energy level, it gives a spectral line in the Lyman series. And when electron jumps from any higher energy level to the second energy level, it gives a line in the Balmer series. So as it is discovered by the Balmer, that's why it is called what? Balmer series. As it is discovered by the Lyman, it is called Lyman series. And when electron jumps from any higher energy level to the third energy level or second excited state or third energy level, so that is called what? That produces a spectral line in the bracket series. As it is discovered by the scientist bracket, it is named as bracket series. And from any higher energy level, if electron jumps from any higher energy level to the fourth energy level, from any higher energy level to the fourth energy level, so that is gives a line in the Paschen series as it is discovered by the scientist Paschen. And if electron jumps from any higher energy level to the fifth level, so that is called Fund series as it is discovered by the Fund. And from any higher energy level, if electron jumps from sixth energy level, that is called Humphrey. So this is discovered by the scientist Humphrey. So here, this Lyman series, it is present in the ultraviolet radiation wavelength or frequency, and it is present in the visible range. This is present in the near IR. This is present in the middle IR. This is present in the FIR. So this is after that. So this is about different spectral lines in a hydrogen spectrum. So here scientist Rydberg calculated the Rydberg calculated wave number of these frequencies by using a formula that is equal to wave number. We already know that is reciprocal of wavelength, that is equal to RH into 1 by n1 square minus 1 by n2 square. So here RH is the Rydberg constant. Rydberg constant. RH is the Rydberg constant. Its value is 109,677 centimeter inverse into Z square. For hydrogen atom Z is equal to 1, that's why we are not going to write. So here it is not a universal constant, it is different for different type of gases. For hydrogen it is 109,677 centimeters, but for another gases hydrogen like species it is 109,677 into Z square centimeter inverse. We already know Z is the atomic number, which means it depends on the type of gas. So here frequency of Lyman series we can calculate it, wave number of Lyman series we can calculate it by using formula wave number nu bar is equal to 1 by lambda, that is equal to RH into 1 by 1 square minus 1 by n2 square. So here n2 equal to 2, 3, 4, 5, 6, 7 like that. So by using this formula we can calculate the wave number of any radiation which is present in the Lyman series. And here wave number of in Balmer series we can find by using the formula nu bar is equal to 1 by lambda RH into 1 by 2 square minus 1 by n2 square. So here n2 is equal to 3, 4, 5, 6, 7. Okay. Next here in Balmer series, so this line is called alpha line, this line is called beta line, this line is called gamma line, and this line is called delta line. So here in Balmer series, if n2 minus n1 is equal to 1, that is called H alpha line. If n2 minus n1 is equal to 2, that is H beta line. If n2 minus n1 is equal to 3, that is gamma line, H gamma line. If n2 minus n1 is equal to 4, that is H delta line. Likewise we can say here. So here H alpha means n2 minus n1, if n2 minus n1 is equal to H alpha, if n2 minus n1 is equal to 2, that is H beta. If n2 minus n1 is equal to 3, that is H gamma. If n2 minus n1 is equal to 4, that is H delta. So here it is the H alpha. So here 3 minus 2, that is equal to 1, that is H alpha. This is H beta, this is H gamma, and this is the H delta. Likewise we have different names. Okay. Next wave number or wavelength of radiation in the bracket series, we can find the RH into 1 by 3 square by 1 by n2 square. Okay, here n2 may be 4, 5, 6, 7 and so on. So here in Paschen series, so here n1 is equal to 3, n2 is equal to 4, 5, 6, 7, and here n1 is equal to 2, and here n1 is equal to 1. And here wave number in Paschen series we can find by using the 1 by 4 square by minus 1 by n2 square. Here n2 is equal to 5, 6, 7 and so on. Likewise we can calculate the wave number of any frequency or any radiation here by using that formula, Rydberg constant. And here next one of the important formula, that is number of spectral lines. Number of spectral lines. Number of spectral lines in a series. When electron jumps from when electron jumps from higher energy to lower energy, higher energy to lower energy, that is n2 minus n1. So clearly the number of spectral lines in a series, in a particular series, in a Lyman series or in a Balmer series or in a bracket in a fashion in Fund series, number of spectral lines. We can find the formula by using n2 minus n1. Here n2 is the higher energy, n1 is the lower energy. Okay, for example, when electron is jumping from fifth level to, so let us take one illustration here. So let us take one illustration here. Number of spectral lines. Number of spectral lines in Lyman series. When electron jumps from fifth energy state. Okay, so number of spectral lines in Lyman series when electron jumps from the fifth energy state or fifth level to the first level, which means here n2 is equal to 5, n1 is equal to 1. Why? Because for Lyman series n1 equal to 1. So here number of spectral lines, that is formula in Lyman series only they ask, that is n2 minus n1, that is equal to 5 minus 1, that is equal to how many lines we can observe? Only 4 lines. So where we can observe that 4 lines? I will show here. So here they are asking number of spectral lines in a particular series only. So here from fifth level, this is the fifth level. So from this fifth level onwards, it is jumping. So it can jump directly to the fifth level to first level. This is first line in the Lyman series, and it can jumps to the second energy level. Then after staying some time, again it jumps to the ground level. This is the second one in the Lyman series, and sometime it jumps to the third energy level. From third energy level to directly first energy level. This is the third one. And sometimes it jumps to the fourth level to directly to the first level. So these are the 4 lines. These are the 4 lines we can observe when in the Lyman series, when the electron jumping from the fifth energy level to the first energy level. This is one of the important question here. And second one is maximum number of spectral lines. Maximum number of spectral lines. Maximum number of spectral lines when electron jumps from. So here they are not telling any series, particular series. Maximum number of spectral lines when electron jumps from higher energy, that is n2, to lower n1 energy. Okay, so the formula is n into n plus 1 by 2, where n is equal to n2 minus n1. So that is n2 minus n1 into n2 minus n1 plus 1 by 2, or we can use one more formula, that is summation of n2 minus n1. This formula also we can use to find out maximum number of spectral lines in maximum number of spectral lines in the hydrogen spectrum when electron jumps from higher energy level to lower energy level. Now let us see, let us take one illustration here. See, calculate number of maximum number of calculate maximum number of spectral lines. Calculate the maximum number of spectral lines when electron jumps from fifth energy level to first energy level. So maximum number of spectral lines we need to calculate here. So the formula, that is n into n plus 1 by 2, or where n is equal to n2 minus n1, means n2 minus n1 into n2 minus n1 plus 1 by 2, or simply summation of n2 minus n1. So here n into n plus 1 by 2, or where n we already know n2 minus n1 plus 1 by 2. So where n2 is the 5, n1 is 1, 5 minus 1 plus 1 by 2, that is equal to 5 into 4 into 5 by 2, that is 20 by 2, that is equal to 10. Means 10 spectral lines we can observe when electron jumps from higher energy level to lower energy level, or simply formula we can use summation of n2 minus n1. So here what is the summation of n2 minus n1? n2 is the higher energy level. What is the higher energy level here? What is the higher energy? 5 minus lower energy 1, that is summation of 4. Summation of 4 means 4 plus 3 plus 2 plus 1, that is totally 10 electrons. And here we have one more formula also, when electron jumps from higher energy level to lower energy level. Maximum number of spectral lines. Here also maximum number of spectral lines, but for special case it is when electron jumps from higher energy level to the first level or ground state. When electron jumps to ground state. So that is the formula n minus 1 by 2. n into n minus 1 by 2. So this is the formula especially for the ground state, when electron jumps from any higher energy level to the ground state. But this formula we can use for any condition, means higher energy level to the second, or higher energy to the ground state, or higher energy to the third state, we can use this formula. But especially this formula is for only when electron jumps from higher energy level to the ground state. So this formula also we can derive from this one. Simply here we can substitute n1 equal to 1 and when you solve that you'll get the same equation. Okay, but they given in some book, this is for the ground state only. For example, when electron jumping from fourth to first means 4 into 4 minus 1, that is by 2, 4 into 3 by 2, that is equal to 12 by 2, that is equal to 6. So by using this formula also we can get the same answer, but they are given the special condition like this. So these are the some problems based on the hydrogen spectrum, and next I will explain about the explanation of this hydrogen spectrum by the Bohr's and Bohr's atomic model and applications of the Bohr's atomic model. Okay, so thank you for listening.